So what we're going to look at here is the process called fractional distillation. So fractional distillation is all about allowing us to separate different liquids. So when we're dealing with lots and lots of, for example, alkanes, if we've got a mixture containing methane, ethane, propane, butane, and so on, and we want to separate those, then that can be very hard because these are all very chemically similar substances. However, fractional distillation allows us to actually extract the individual alkane out of that mixture that we are after. And so what it does is it separates these liquids by making use of the fact that they all have different boiling points. So basically most of our organic substances that we deal with are quite volatile. And so what we need to know, a very important factor in this process, a very important sort of property that is utilized in fractional distillation, is that if we have a vapor of this mixture of volatile liquids, then this will contain a higher concentration of the substance with the lowest boiling point. So if we have say three different substances, A, B, and C, and they're all volatile, and we heat those three substances, then we'll say that substance A has the lowest boiling point, which means it evaporates at the lowest temperature. And that means that it's going to be, if we have this vapor, if we have all this vapor at a given temperature, and A has the lowest boiling point, then that means molecules of A are, say, given that this vapor is at a given temperature T, and we have substances A, B, and C with boiling points of TA, TB, and TC. Well, if TA is the lowest, so the boiling point of A is the lowest of the boiling points of these three substances, then that means the temperature of our vapor is much, much more than temperature A. The difference between the temperature of the vapor and the boiling point of A is greater than the difference between the temperature of the vapor and the boiling points of our other substances. And what that means is that this will contain a higher concentration of substance A. That's what it comes down to. A has the lowest boiling point, it evaporates the easiest, and therefore any heated vapor containing A, B, and C will have a higher concentration of A. So that is basically the principle by which fractional distillation works. So here we have a fractional distillation column. So down here we have the bottom of our this is our distillation flask, which contains a mixture of volatile liquids. So these may be, the different alkanes that we discussed earlier. So this may contain methane, ethane, propane, butane, and so on. We place this over a heating element. So we heat this mixture of volatile liquids. And so this bowl here is called distillation flask. So we heat this mixture of volatile liquids in order to create more and more vapor. So obviously, as we create vapor out of this mixture, this vapor will contain a higher concentration of the substance with the lowest boiling point. And as we move through this column, this vapor will rise because we know that hot air rises. As this vapor rises, it meets lots and lots of glass beads. This column is filled with glass beads. So what happens is our vapor, the different elements of our vapor, condense on these glass beads as they make their way through them, and then after they condense, they drip back down lower in the column. As they drip back down, they are reheated and they evaporate again and move up. And so basically we have this continuous cycle going on of condensation and then evaporation and so on. So another important factor to be aware of is that as we move up the column, the temperature decreases. So as we move up the column, not all substances will remain as vapor because the temperature is getting lower. So as the temperature may get below the boiling point of a substance, that boiling point will condense on the glass beads, drip back down, and then as it drips back down, it will get hotter. It will get to a hotter part of the column and evaporate again and move back up. And so what that means, as this process repeats itself again and again and again, it basically means that this hot vapor at the top, uh, the concentration of the substance with the lowest boiling point gets higher and higher in this vapor at the top. So the vapor at the top gets purer and purer as the other substances in the vapor are condensed and re-evaporated below it. And so we kind of get this really nice separation of all the different substances in this in our mixture due to the continual repeated cycle of evaporation and condensation. And so eventually the top gets very pure. The top is very pure and provides a very pure sample of the substance with the very lowest boiling point. And so what we do is that once stuff gets to the top, obviously as the longer we run this process for, the hotter the whole column gets. So over time, the top of the column gets hotter and hotter, and so the stuff that's condensing at the top of the column can be collected. And so first we might have the substance with the lowest boiling point condensing at the top and dripping out here. Next we'll have the substance with the second lowest boiling point condensing at the top and then dripping out here, and so on. And so what we can do is, if we already know the boiling point of the substance that we want to obtain, say we might want to obtain a specific alkane, and we may already know its boiling point, and therefore what we do is we collect the stuff that condenses at the top of the column at temperatures very close to this boiling point. So what we do is so this is, I guess, sort of the key part, the key ending to this process, is that we're obviously, if we're looking for a specific substance, one individual substance in that mixture, then we collect the condensation at the top of the column over a range of temperatures that are very close to the substance of interest. So maybe we want a substance which has a boiling point of 52 degrees. Then we will collect the stuff that condenses maybe at a temperature between 50 and 54 degrees. So if we write that out, maybe we have a substance that has a boiling point of 52 degrees Celsius. Then we can collect the condensation that is produced between 50 and 54 degrees Celsius, and that'll give us a relatively quite a pure sample of this substance with a boiling point of 52 degrees Celsius. So that is how fractional distillation provides us with a good separation and a way to extract individual substances from a mixture of volatile liquids. However, it's also important to be aware that this process is not perfect. Although we may collect condensation over a very small range of temperatures close to the boiling point of the substance that we want, it's going to be very difficult for us to obtain even then obtain a 100% pure sample in this flask. So what happens is our substance of interest condenses at the top, drips through here, and then we put a new flask on through between 50 degrees Celsius and 54 degrees Celsius. When the temperature at the top of the column is between those two temperatures, we put a new flask on and therefore collect just the substance that we want. However, it's very unlikely that we will obtain a completely pure sample. It's very hard. We can obtain relatively high purity. However, usually we'll be looking at something around 95% purity. So there will be some other substances from this mixture of volatile liquids that will make their way into our flask here, into our collection flask. And so we call the stuff that we collect at the end, we need to give this stuff a name. So we collect some stuff at the end, and we call that stuff that we collect at the end the distillate. So it's obviously important terminology there. We collect the stuff that we collect is called the distillate. So that is, at this stage, all you need to know about fractional distillation. Now we'll have a look at a brief example, which is very kind of just a quick, brief look at the ideas of behind this process. So if we've got ethanol, and we've got propanol. Which of these will be collected? Say we've got a sample containing both of these. Which of these will be collected first in our fractional distillation column? Well, these are basically, we'll say that the propanol that we're dealing with is one propanol, so the hydroxyl group is on the end carbon in the 3-carbon chain. And so these two molecules have the exact same structure, except propanol has an extra CH2 group in the middle. So that means both of these have this polar hydroxyl group, and so both of these molecules are polar. However, propanol is in fact less polar than ethanol because the non-polar chain in the propanol molecule is longer than that in the ethanol molecule. If we were to draw these two out, then we would have ethanol looking like this. The hydrogen's bonded like that, whereas propanol would look like this. And so, while both of these molecules both contain this very polar hydroxyl group, the polar hydroxyl group is quite smaller in size in comparison to the rest of the molecule in propanol, because propanol has a longer alkyl chain, has a longer non-polar string of carbons out here. It means that the molecule as a whole is less polar. And what that means is that it will have a lower boiling point. So propanol will be collected first, and after that we'll have ethanol being collected, because ethanol is more polar and therefore has stronger forces of attraction between with other ethanol molecules, and therefore ethanol will stay as a liquid for longer as it's heated. So propanol will be collected first and ethanol will be collected second.